by 0. Now I could do it maybe 25 if I talk really fast. Most of what I'm going to be doing is pointing to things on here. It's pretty much self-explanatory. But remember that you first need to understand your need-to-know list for the anatomy of this. So you guys have this on Canvas. It is really, really damn short. You can learn this in an hour, right, which is really nice. To help you with all the various parts that we're talking about tonight, if you scroll down, there's this page that become a little more obvious and understandable as we go through tonight's lecture. But basically, first pass of the basic regions of spinal cord, then a little more specificity to the parts of a spinal cord found in there. Then you scroll down to page 3. What does that say right there at the top in big bold letters? All right, because I don't have time to talk about spinal thalamic pathways, so I'm eliminating that from this. So don't worry about trying to answer all of these. Right? If you're going to go more into physical therapy, OT, or PA school, I would be able to do this, but it's a reference for you in the future. Because understanding the actual pathway and which part of the spinal cord sends what kind of a path or what kind of information is kind of important, and we don't have time for it this summer. So, to help you with all these, realizing that some of you might be feeling a little brain fried, I need you at least, before you run out of here like the house is on fire, photograph all the various models of the spinal cord. So you can begin looking at this tomorrow if nothing else, right? We have 3 different versions of these. They're down here on the shelf, so photograph them from different angles so you can begin studying them. Now, in terms of your spinal cord actually ends right about L1, what's called the corona medullaris region. So, right about here. That is the official end of your spinal cord. There's no longer a cord from that point onwards. It becomes more of what's called a horse's tail. We have this term here called china or cauda equina, which means tail of the horse. And the idea is that when your cord, if you just make it end like this, just to be kind of crude, I start getting these long filament structures. That's really not working very well. It was working well. Yeah. I'll fix that later. These long little branches. So picture this. Picture the ascent of a horse. The rump of the horse is the conus medullaris. The tail of the horse is the cauda equina. I have these long filament nerves coming off of the rear end of my spinal cord. And that's going to be beneficial to the idea of taking a spinal tap. But all of this is cauda equina, and there's the official end. And that's because your spinal cord stops growing at age 4. Your vertebral column does not stop growing. So as my vertebrae get thicker and thicker, my cone used to be down here, but as my vertebrae get thicker, I end up pulling the base of my spinal cord higher and higher up. And these spinal nerves have to grow along with it. They start to extend like tendrils almost.
So underneath that big piece of length, at the top,
Well, I mean, everything's growing, but the actual cord stops. All we have down these long projections of spinal nerves coming off of it. A part of your task for the anatomy part is to remember or identify the anterior part from the posterior part of the spinal cord. And there's 2 ways you can do this. One is look for the posterior median sulcus or the anterior median fissure. And sulcus and fissure sound familiar to me. Like things on the brain. What's that one that goes right down the middle lengthwise? And how is that different than the little crevices between my gyri? It's deeper, right? So I'm looking for a more pronounced gap. If I go over here, right, that's the anterior median fissure. That is a sulcus. And if I can see the fissure, I know it's the anterior portion of my spinal cord. If I only see the sulcus, then I know it's the posterior portion of my spinal cord. But that takes a little practice. There's a way more obvious, like hello, no-brainer way of identifying the anterior from the posterior. Look at this model of a cross-section of your spinal cord, and I see a tan H. Look at the H. Look at the H here, 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 and there. And what is similar to that H in each of those different images?
Goes all the way on the posterior side?
Goes all the way to the posterior side, and it doesn't go to the edge on the anterior. That's how you tell. Posterior, the gray matter always goes to the margins of the spinal cord. So if I see this, I know that's posterior. I can confirm it with a posterior median sulcus if I like. Right? But the fact that I see this going to the edge, I know it's always posterior. So they're going to divide the spinal cord in half. An imaginary line going all the way through here. Everything on this side is posterior. Everything down here is going to be anterior with this. Now we can take your spinal cord and think of your spinal cord as a big, tall building. There are floors in the building. Well, we can call each floor a segment. So we're going to have 34 different floors or 34 different spinal segments. And each segment contains these three things, right? A pair of dorsal root and ventral, or dorsal root and dorsal ganglions, which we'll go over, a pair of ventral roots, and a pair of spinal nerves. Well, that's this stuff right here, right? This is my dorsal root, and there's the rest of my dorsal root. That is my dorsal root ganglion, and then there's my ventral root, and there's my spinal nerve. I'm going to have one spinal nerve on this side, one spinal nerve on that. A ventral root here, and I got two of each, one on each side. Part of the question is, who actually remembers what a ganglion is?
It's a collection of neural cell bodies in the peripheral nervous system.
Yeah. So what's in there? A collection of neuron cell bodies. I know that. All right? And we'll help you visualize that in a moment. But this is where terminology is going to really help you remember what it is or where it is. Remember that dorsal is another term for the word posterior, and they're interchangeable. Books will either call this the posterior root or they're going to call it the dorsal root. They don't do that, however, down here. I very rarely see the word anterior root. It's mostly ventral root, but anterior and ventral are interchangeable with these. All right, so I've got the gray, the white portion of my spinal cord, and I have the gray portion of my spinal cord. In other words, gray matter, God, dude. White matter, it's been a long day for me. White matter and gray matter. My question to you is, why is it called white matter? What makes neural tissue white? It's myelinated, right? Remember, it's only the axons of a neuron that are myelinated. So you know what's in there, myelinated axons. What makes gray matter? There's two things you want to think about. Well, so go back to the myelinated neuron. Is the entire neuron myelinated? What parts are not myelinated? The somas. So that means I could have the somas of myelinated neurons in here, and their tails just go, or their axons just go into the white matter. Or interneurons. They're so short they don't need to be myelinated. So I can have entire interneurons in the gray matter, or just the somas of myelinated neurons. Wherever you have gray matter, you can think that all the time. Somas of myelinated, or the entire structure of an interneuron. All right. Now this you actually already know. All right. This is a repeat. You have meninges of the brain. We have meninges of the spinal cord. You have the same layers. All right. Dura, arachnoid, pia, subdural, subarachnoid, cerebrospinal fluid. It's all the same. What I want you to think about, though, is with this meningeal tissue wrapping around my spinal cord, it's also wrapping around, and you begin to look at this and go, wait, I recognize that thing right there. That is my dorsal root ganglion, and there's my ventral root. All right, it's just this thing, there and there. Because there's, what is this thing called right here, this part? And this right here would be the body, right? So I'm looking at someone's back, and their organs would be on this side. But the meningeal tissue is going to come off of the spinal cord, and it's going to wrap itself around these nerves, right? Especially as it passes through, what's that space between two vertebrae? Intervertebral foramen. And as that nerve comes out, I'm still wrapped by the meninges. It'll finally taper off to nothingness, but it'll seal shut. That way my cerebrospinal fluid in the subarachnoid space, right, can wrap around the spinal cord. It can wrap around these ventral and dorsal roots. It can wrap around the spinal nerve, and then it finally just tapers. if I need to bathe all this stuff in fluid. But eventually it does stop. But there is one big difference. Think of the skull, think about the meninges, and the dura mater and the cranium. What are the two layers of the dura mater? So, dude, don't test me now, for Christ's sake. We just had an exam, right? You have two layers, right? The periosteal and the meningeal, right? Otherwise known as the endosteal layer. Why was it called periosteal? Because it's up against the periosteum of the cranial bone, right? It's like wallpaper on the inside of your cranium. If I could take someone's skull, it would be attached to this layer of my bone right there. There's nothing between the dura mater and my bone. That's not true over here. Here's a cross-section of your spinal cord. And I realize, right, so there's the dura mater. That's this layer right there. Got that. There's my subdural space. There's my arachnoid, subarachnoid space. My pia mater, all systems go. I totally get that. But then John has this damn red arrow. What is above the dura mater in the diagram? Adipose. That means there's a space there. If that's called the subdural space, what should I call that space? How about an epidural space? Oh, how many of you heard of an epidural? That's where you get one, because it goes into that space. But and pay attention to the picture, right? Is the epidural only found right here in our diagram? No, remember, it comes all the way around. So that's epidural too. It's not subdural. Right? This is still epi, but it's filled with adipose tissue, mainly as a way of protecting the spinal cord in my vertebral foramen. But it's also a nice handy thing that I can come in anteriorly with a needle, and I can inject some local anesthetic and maybe anesthetize that spinal segment so I don't infect your entire body, but I can give you a local and block you from that point on down. It can either go into the fat tissue and it'll work its way in, or I can feel the resistance break and just got to learn how to stop the needle because you don't want to go in there, right? Because that's my spinal cord, but I can deposit the medicinal effects right along in here. And that's why it's called an epidural. But there is a lot of space here. So I do need to stabilize your spinal cord from wobbling and going up and down. So we have these ligaments called the denticulate ligaments that connect from the pia mater to the dura mater. And they have to stabilize the lateral motion of your spinal cord so it doesn't wobble all over the place within it. We're just going to use the denticulate ligament for this. It's going to go from the pia mater to the dura mater. Now we can talk about that because the pia mater is where it starts, right? And it's going to end in the dura mater. But we got to go back and talk about the longitudinal way of stabilizing your spinal cord, the up and down motion. And what I'm trying to say here is that the dura mater joining the foramen, where's the foramen magnum? It's in your skull, right? So you picture the dura mater around your brain. It's going to pass through the foramen magnum. And as it comes out here to then wrap around the spinal cord, it's going to fuse to the margin of the foramen magnum as an anchoring point. That way I can prevent the spinal cord from going up and down. I'm going to do the same thing though. This is where I wish I had two projectors. So there's under my skull, but this is at my sacrum region. Right? Go back to the very first picture. Right down here called the filum terminale. There's connective tissue from the pelvic bones to all these fibers of your cauda equina, like spider webs in a sense. And that helps to anchor my cauda equina down here, and then around the foramen magnum up in there. And that's my longitudinal stability. By taking advantage of the filum terminale and then the margins of my foramen magnum. All right, now we're going to get just a little more specific. I know I've got white matter and gray matter in my spinal cord. We want to create zones like neighborhoods, and they're very logically named, right? There's my anterior median sulcus. Fissure. Therefore, I know this is the anterior portion, so let's call this the anterior white column. If that's the anterior, let's call all of this the posterior white column. And if that's the lateral side, let's call it the lateral white column. Very straightforward. So white columns mean white matter in the spinal cord. Now we do the same idea for the gray matter, but we don't use the word gray columns, which would be a little more logical. They look like horns to early anatomists, so I call them gray horns instead. So we're going to have an anterior gray horn, a posterior gray horn. We got two on posteriors, we got two anteriors, and then we have a lateral gray horn. Got that, not a problem. So I know that gray horn means the gray matter, and the white column refers to the white portion. But now we want to subdivide it. And we want to look at what they're trying to show in terms of the anterior gray horn is comprised of what? Motor nuclei. And the posterior is comprised of sensory nuclei. So if I get a piece of shrapnel entering this portion of my spinal cord, I'm not going to test sensory information. I'm going to test their motor ability, right? I'm going to test sensory up here. I'm not going to test motor. But look how it's laid out. The anterior portion of the anterior gray horn is comprised of somatic motor nuclei. So what are nuclei? Well, they're collections of neuron somas where? In the central nervous system. Remember, that means your brain and spinal cord. So in my mind, I'm picturing motor nuclei, motor neurons. Their somas here. And their axons are going to come down over here. So to practice this idea, let's draw out your spinal cord. And I would draw it out as well as you guys practicing on the diagrams we have. But I'm going to just make a nice big black circle. All right, and then I'm going to go over here and draw my attempt at a dorsal root. There's the ganglion. Coming back to the root, we're going to come down here to about here. Then I'm going to draw a ventral root coming here, coming there, and then this is going to be spinal nerve. I can label this the dorsal root. That's that. I can label this a ventral root. And then my attempt at doing the posterior gray horns, no laughing. This will be my anterior horn. Coming down like this. But it's supposed to be uniform, it's not. All right, we'll come up here. We'll just do this. All right? This is why we label things. So I know what the hell is I'm looking at, right? Those are my posterior gray horns. See how I didn't bring it to the edge, but I did bring it to the edge over here. Right? And that's going to be my little lateral gray matter, my lateral white column, anterior white column, posterior white columns. But then we want to look at what we have. That's ganglion. And that tells me the collection of neuron somas in that structure. And I know that the dorsal root is associated with sensory signals. So we're going to have sensory on this side. We're going to have motor down here. Well, sensory, I remember from John's talking about the different ways of organizing neurons. I could do it by function. You can also do it by structure. And I remember that there's a certain type of structural neuron whose role is in a sensory fashion. That's a unipolar neuron. So I remember unipolars kind of look like this. Right? That means their axons have to come down here and go this way. And then these guys are going to come in and they're going to go into here. Where they go, it's going to vary. But that is a unipolar neuron. And I know that going into my posterior, I'm going to have two different types of unipolar neurons. So I'm going to show two different types of unipolar neurons. I'm going to have a purple one as well. And then the black could be visceral. You can make the purple somatic if you like. I don't care which one it is. But, you know, purple could be somatic and the black could be visceral. That means I have a visceral unipolar neuron and a somatic unipolar neuron. I have a somatic and visceral sensory pathway. I do the same thing over here. We'll change colors. Let's go, how green are you? That's pretty green. We'll put it in this motor neuron there. It's a multipolar neuron, and its axons are going to come through here, come up and go through here. I've got both somatic and visceral, so we'll show the other possible motor neurons that are in here. And their axons coming through here. Yeah. It's okay if they cross over for a moment. So now I can visually see that that's why it's called a ganglion. And I can recognize now the fact that, I mean, if you want to be really technically correct, we'll do this. So we can color code it. We'll make the green ones the visceral. Those are closer to the lateral gray horn. And the blues we can make somatic. Oh, wow, taking that one home. Okay. But now let me ask you this, right? I can see the two different types of motor neurons in the ventral root. I can see the two types of sensory neurons in the dorsal root. How many neurons are in my spinal nerve? How many colors do you see? You got 4. It's called a mixed nerve. It's comprised of both sensory and motor. This is only motor. That's only sensory. So the signals in this that we're going to learn, that the information in the dorsal root is going to go this way, right, toward the central nervous system, and information is going to flow in this direction from the anterior gray horn through the ventral root. Now I know the flow of traffic with this. Guys, okay with this part?
So bipolar neurons are also involved in sensory, right?
Mm-hmm.
So, but they're not a part of the...
No, you can find bipolars in the eyes and some other places, which I'm going to cram down your throats on Monday.
Yes.
Yes, you are.
Okay, now, think about the structural organization of muscle tissue. What's the name of the tissue that wraps around the outside of a muscle? There's epimysium, right? Perimysium, endomysium. We had bodies, we had fascicles, we had cells. Take that knowledge and go, it's the same thing for a nerve, but I'm going to change the names. It's going to be epineurium now. The neurium refers to nerve tissue. So I've got epineurium, perineurium, endoneurium, no big deal, right? Pretty similar in understanding. I have the only difference is this big thing is one big honking nerve, but so is this. This is also just a smaller big nerve. This, well, that's a single axon from a single neuron, but it is a nerve. It's just a single-celled nerve. So they're all nerves, but nerves come in various sizes, and we're just organizing them. So if you think about this, could be like your sciatic nerve, coming down to your femoral nerve, coming down to maybe the nerve that senses the underside of your big toe, all right? And each one is wrapped by a different layer of tissue to maintain that packaging. But there is one little bit of unique difference. If you guys are to peel away the endomysium, you get down then to the sarcolemma, right? The membrane of that cell. If I peel away the endoneurium, do I get to the membrane of that cell? No, I get to that stupid myelinating cell called a Schwann cell. Then if I unwrap that little bastard, pardon me, then I get to the axon, right? The membrane of that cell. Unless you're poking into a node in that context. So there's still one additional layer of wrapping that's covering these guys up. So if you do a needle biopsy, I could potentially have to go through the epineurium, the needle has to penetrate the perineurium, has to go through the endoneurium, and maybe even penetrate a Schwann cell, and then get to the actual membrane of my neuron. Those are the layers of things I'd have to pass through. Well, let's take all these nerves and create regions of them. Now, we have this, and then we have this. This is an FYI. Do not memorize this. Do not memorize this. This is a visual of what plexes are, okay? Now, for a plexus, we have 4 major groups. Cervical, I think you can figure out where that is, right? brachial will be your shoulders. You're going to have a lumbar, pretty sure I know where that is, and my sacral. What I have given you guys is the most common nerves associated with those plexuses that you do need to memorize, right? Just the names. You don't have to find them on a model. It's just intellectual anatomy. So the most important one coming out of my cervical plexus is going to be, where does the phrenic nerve go to? The diaphragm. Yeah, okay. You guys all know that, right? Yeah, okay. The brachial, though, right, is comprised of the axillary, median, ulnar, and radial nerves. So if I'm complaining of a dull ache in my radial nerve, right, I may want to go examine my brachial plexus to see if there's any nerve impingement there, any spasms of muscle tissue, compressing this, which will lead to one of these guys, or maybe even all of them, having a general dull ache. Lumbar, the most important one for us, is the femoral nerve, and for the sacral, it's going to be the sciatic, the tibial, and the fibular nerves. Just know them intellectually, like a list. Well, does anybody know what a plexus is? What does that mean? It's not a connection.
It's where all the everything joins and it goes back and it parts. And they're all separate tracks, but they're woven together like a net.
That last little part. Think about when gals make ponytails or braids, right? It's a plexus. You're braiding, you're weaving together, joining together other nerves. So it'll look somewhat like this. And this is why it's a not need to memorize idea. Let's come down to your sciatic nerve way down here, the really big one. My sciatic nerve is actually comprised of branches of S3, S2, S1, L5, and L4, but they're being braided together to form a larger structure. Right? Look at this nerve right here called the lateral cord. Let's do, the lateral cord, the posterior cord, we'll do that one. It's the biggest one for the complex. What nerves do I find joining this? Well, let's see. T1, C8, C7, C6, and C5. They're all coming together to contribute to that nerve. And that's what a plexus is, right? It's this braiding of nerves to form a larger structure. You guys don't need to memorize any of this, but if you need access to it, that's there in the future. If you're going to be working with maybe orthopedics or PT. But all of these nerves are actually named by their spinal segment. And we need to learn the IUPAC rule for naming nerves, right? It's really simple, right? If I have a nerve found in my cervical region, right, how do I name it? The spinal nerve name comes from the cervical vertebrae immediately inferior to the nerve. So I name the nerve for the vertebrae found below it. So it would look like this. If that's my first cervical vertebrae, then what's the name of that nerve? It's called the C1 nerve, because I'm naming that nerve for the vertebrae found right below it. All right, that makes sense. And then why not just keep it that way? Oh, God knows why. They flip it on you. All right? For thoracic and lumbars, they literally flip it on you. Now I'm going to name the nerve for the vertebrae found above the nerve, not below it. You can do it for the name above. You got to just memorize that. It's just like, great, thank you guys for doing that to me. All right, so I would memorize one, and then remember the other one is just the opposite. It's a nice way of keeping it straight. All right, so now we know what plexuses look like, and I have examples of them. All you need to know is the names of them, right? And then intellectually, the major nerves served or coming from those major plexuses, but no diagramming, no anatomy for those.
Wait, wouldn't two of them have the same nerve or have the same name?
No, they don't. You actually have 8 cervical nerves and 7 cervical vertebrae.
Okay, that makes sense.
That's what they make it. Very good, George. All right, now we got dermatomes. All right, again, do not memorize the pattern. All right, maybe I'll make George do that. All right, but you guys don't have to. But here's the key to it. If I go to a neurologist, he thinks this little pasta wheel with little spikes on it, and he runs it right along the posterior side of my forearm, right in here. And I'm waiting for him to do it. And I said, come on, do it. I said, I've already done it 3 times. Oh, really? I couldn't feel a damn thing. Well, then he knows what nerve to go look at. Go to the segment of C7 And maybe I've got a nerve, maybe I've got a vertebral disc that slipped or something. But he knows the problem is coming from C7. And all these various regions of derma, meaning skin regions, relate to, right, specific pairs of spinal nerves. And they would memorize this pattern. You guys are not. All you need to know is what a dermatome is, right? So if I were to touch the palm of my hand and not feel a thing right there, I picked the same spinal nerve. How interesting. Okay. Then I know to go look at then my C7, because I can't feel that whatsoever. Okay. Almost at the end of this. Reflexes. Yeah, they maintain homeostasis through a rapid. What the hell does that mean? Think of it as keeping you safe at a subconscious level. So responding to stimuli in a subconscious fashion. You don't have to be aware of doing this. And your simple reflexes you're going to see don't involve your brain whatsoever. It's totally left out of the whole conversation, which is good because it means a faster response. And we're going to show you examples of these. Now, in terms of reflexes, there's actually two types. There's the innate, which means what? What does innate mean? You're born with, right? Like your innate immune system, right? There are several innate reflexes that we're going to be showing you that help you to survive without you having to be taught how to do it. And there's some really fun ones that disappear as you go through life. Stefan, do you remember one innate reflex that I did to your daughter this afternoon?
Oh, I can't remember what you called it.
I put my finger, he has a 4-month-old? Yeah. Cute as hell. Put my finger in the palm of her hand. What did she do? She grabbed it, right? When did you teach her how to do that? He didn't, right? Why do we have that reflex anyways? It's a grab, but why do we have this automatic ability to grab things that are put in the palm of our hand? Long time ago.
Hang on to mom.
Hang on to mom. Look at primates and lemurs, right? The chimps are nobody taught the chimp how to do this. And why is that a good thing? It frees up mom's arms. She can now either fight off nosy relatives or predators or carry more food. We still have that innate ability, right? There's a really cool one that you can do with babies. So I could take your 4-year-old daughter and just toss her in the pool. Boom. She'll do a parachute pose and she'll hold her breath and start to swim. Wow, that's pretty freaking cool, right? Now it'll go away after a while. But the cool thing about us is that no one has to teach you these very simple subconscious responses to stimuluses. We're going to go through two very simple ones.
Can they still be like taught or worked on and improved, or?
Not for these, no, because they're pretty wired to begin with, right? But these, you can, right? Acquired reflexes or reflexes that you're taught. So how many of you, did anybody here do martial arts? All right, how about sports? Oh my God, okay. Did your coaches ever tell you don't think about the situation, but respond, react to the situation? That's what this is. Don't think, just respond. Right? And the more training you do, right, the more you can respond to that scenario of offense or defense. And you just know where to go. You don't think of it, you just do it. Right? That's what this acquired reflex is. Well, in terms of our innate ones that we're going to focus on, all right, we're looking at two major groups of reflexes. Because if you remember our little conversation, you may not, but you will by tomorrow, the idea of taking our nervous system and dividing it into two major, big, gigantic, vague categories, central and peripheral, right? The peripheral divided into afferent and efferent, right? Sensory versus motor. And I told you guys in the video that both of those, the afferent and efferent, have two subdivisions. They both comprise of a somatic and visceral aspect, right? Somatic means my body, all right? Visceral refers to my organs. We have two levels of innate reflexes, both from my somatic system, we're going to talk about tonight, but also your visceral organs, right, that are comprised of smooth muscle tissue, have a response, a reflex pattern. How many of you here have ever, let's say, eaten some bad oysters? What happens about 6 to 12 hours later? Who told you how to puke? Nobody did, right? No, your body just knows how to contract those muscles. It's a reflex due to the toxins in the system. Well, peristalsis is the word we're using for the contraction of smooth muscles. And when you contract smooth muscles, things move from point A to point B. Then when you guys are in 242, we're going to teach you about swallowing. There's a peristalsis to move the food down your esophagus. There's a peristalsis to move things through your small intestine. There's a peristalsis to move it into your large intestine. And you have all these little reflexes like enterogastric, gastroenteric reflexes. There's also a reflex that says, all right, get this crap out of me quickly. And that's where you got it going at both ends, right? So we call this peristalsis. Now, to go up this way, what do you guys call it? Barfing, vomiting, upchucking, porcelain god. We also call it reverse peristalsis, right? Because it's going in the opposite direction. And no one tells you that you have, you just wake up going, oh my God, where's the toilet? I got to run to the bathroom. It's a reflex due to the toxins.
Is burping also one?
And that's more of a pressure system with those.
Is that what you wake up for your tube?
Yes, you don't drown, hopefully, in that context. But if you think about it, think about how cool that is. You're going to bed just fine, 4 o'clock in the morning, and oh God. Holy, you don't have to think, you just know you got to run to the bathroom, right? And hope to God you make it before anything else happens. Now we've got this. All right, complexity of minute reflexes. We're talking about these reflexes. We're not going to talk about these. Well, I have 2 levels of complexity. The simple ones and the more complicated ones. First, learn that. That's easy. All right. Now, why is it called simple? Because it involves one synapse in the pathway. That's why it's called a monosynaptic reflex. There's one synapse in this reflex. We're going to go look at it. We'll come back and do the more complicated one. So, what does it involve? Sensory neuron innervates directly with a motor neuron. Okay, well, that's this picture right here. The red one is my sensory. Oh, look at that. It's a unipolar neuron in a dorsal root ganglion. All right, this is going to become automatic reflexive knowledge to you. Now, look where it's going. There's my spinal nerve to my dorsal root ganglion, through the rest of the dorsal root into the posterior gray horn, going through and entering and ending at a synapse with a motor neuron, a somatic, by the way, motor neuron in my anterior gray horn. That's my only synapse. Therefore, it's a monosynaptic reflex. The way this works is that you have these nerve endings embedded in the muscle tissue, right? By the muscle cells, the myofibers. And when you take a little reflex hammer and you actually press down on the patellar tendon, unbeknownst to you, you're actually stretching that tissue by just a couple of millimeters. But that freaks out those cells. They don't know any better. They're afraid you're going to be torn apart. So it goes, okay, we need to conserve ourselves. If I'm being torn apart, what do I need to do? I need to contract so I don't get torn to pieces. So as soon as you hit that, right, there's a rapid action potential that goes through this. They release neurotransmitters, creating an action potential that sends the action potential. See, what neurotransmitter would be released here? Acetylcholine, right? And what's the name of the enzyme that breaks down that acetylcholine? Acetylcholine esterase, yeah. And bingo, I got a muscle contraction, right? It's nice and simple. That part makes sense? Okay. Now, type of axons involved. These axons here are called type A neurons. It's another way to classify neurons. We have them by structure, we have them by function, we have them by the type of neurotransmitter they release, and also know how fast they propagate or send neural signals. Type A's are your fastest, and they send roughly at about 268 miles an hour, which doesn't seem maybe very fast, but if I'm only traveling 2 feet, that's pretty fast for 2 feet of distance, right? It involves for a really rapid response to stimuluses. The other ones that we're going to focus on are going to be type C fibers. So type A's are 268. Type C's are a whopping 2 miles an hour. That's a big difference. 268 versus 2. So how many of you ever had the experience of about to fall flat on your ass and you throw your arms out really, really fast? Right? That's type A fibers, right? Your brain saw you're falling. Let's quickly put you in position to protect yourself. Right? So to give you an example of this, a couple of years back, I was walking out of my apartment. I'm on the 3rd floor, and we have these concrete steps and a concrete rough gravel pathway. And I was walking down, doing what I tell you guys never to do, which is looking at my phone, going. Have you ever had the experience where you swear to God there's one more step, but there really isn't? Right? And so you just go ass face first, right? And I went ass face first, boom! I heard, oh my God, my phone. Oh, thank God, it's okay. All right, that was my first thought. Stand up and look at my palms going, oh, wow. And then the nerd just kicked right and went, oh my God, that's so freaking cool. Look at that. I can't feel it. It's all, there's no blood, this is freaking, this is an example for class. This is fantastic. All right? And then I know I'm going to walk up the stairs, get into my car, I'm going to go, oh shit, now this really hurts. Oh my God, it stings and it burns all at once. Well, how many of you ever had the experience of turning on the tap for the dishes, turn on some cold, turn on some hot, and you turn the hot just a bit too much and didn't realize it, but your hands are in there, all of a sudden now it burns and you pull your hands out, but it gets hotter even though your hands are no longer under the water. You ever had that experience? Try it at home. Okay? Put the hot water on, pull it out, and you go, man, it's hotter now than it was under the hot water. That's a type C fiber. You can literally, physically see the difference in how fast the signals get sent. So, okay, I understand type A's. Really fast means I can quickly respond to stimulus. I'll save my ass. Why would I want a really slow message? The idea is that when I recognize danger, I don't want to panic because of the danger. I want to go, okay, yep, my mouth or my arm is in the mouth of a mountain lion. Okay, I need to get my hand or my arm out of its mouth. Because if I felt pain right away, I might actually try and pull my arm out and cause more damage. So evolution says, let's make you be aware of the scenario, but not feel the intensity of the scenario. We'll let the pain set in a couple of seconds later, after hopefully you removed yourself from the danger. And so that's why type C fibers are really important, because they have a very slow propagation of signals. That gives your brain time to go, yeah, dude, your hand's in the fire. You may want to get your hand out of this, all right, instead of just panicking and maybe pushing your hand into the fire even worse. So that is a monosynaptic, right? No interneurons. The sensory neuron went all the way down to the anterior gray horn, right? Kind of went all the way down to here and talked to the blue dude. But now we have the more complicated ones, right? And first, look at the name, right? They're called polysynaptic. What does poly mean? It means many. So there are probably many synapses involved in this pathway. So there's monosynaptic. Now we're looking at polysynaptic. It's called the withdrawal reflex, to pull your hand away from maybe a hot object. And let's go look at this. But look at the thing I want you to focus on. It's going to involve interneurons. Oh, God, what the hell are those things? I need PSP, IPSP, that means, yeah, it means GABA, acetylcholine, potassium chloride, making membranes more positive or more negative, but not reaching threshold. All right, keep all that in mind, all right, as we talk about this. So, you grab the handle of the cast iron fry pan, left on the burner on high for a while. You touch it, pain signals, traveling through, again, there's my unipolar, which means it's sensory, right? Through the dorsal root to the posterior, but now look where the sensory is, right? The synapse is right there. Whereas before, whoops, it was down here in the anterior, but now I'm in the posterior. And that white dude is an interneuron. It's going to relay the message. But now who's it relaying it to? Well, if I want to pull my hand efficiently away from that hot pain signal, I need to do two things at once. Contract one set of muscles and then inhibit the opposite group, the antagonistic group. So I need to send the nerve signal through here, Neurotransmitter release, create an action potential. Neurotransmitter release, create an action potential, make my biceps contract so I can pull my hand up, but I don't want my triceps trying to contract. That'll make my forearm go down. So I need to shut them up and make them work. And to do that, my interneuron has to talk to yet another interneuron, this little black dashed one. And that little black dashed one will then talk to the blue dashed one. And the blue dashed one isn't going to send a message to the triceps. Now, I'm going to have you guys try and figure this out. But here's one thing to think about for us at this level of physiology. A neuron can only release one type of neurotransmitter. All right? Any one neuron can only release one kind of a neurotransmitter. So, if that's a motor neuron, isn't it? Oh my God, you guys are going to say yes, right?
Yes.
Isn't that going to a muscle, therefore it has to be a motor neuron? All right. Now, if it's releasing acetylcholine down here, it must have been activated, right? So how can I activate that motor neuron? Well, whatever neurotransmitter was landing on the somas had to come from that white interneuron. Well, whatever that neurotransmitter is, it has to use the same one for that black one over there. It's only one kind of neurotransmitter for each type of neuron. So the best way to figure this out is work backwards. If I don't want this motor neuron to work, then how could I inhibit its ability to form an action potential? What neurotransmitter must be released right here onto the soma? And that neurotransmitter would have come from that black dash interneuron. So what are you releasing? Because you had to be activated to release your neurotransmitter. And if you were activated, what neurotransmitter must that white interneuron have used to activate both that motor neuron, but also simultaneously that black dash interneuron? And then that black dash one gets activated to make sure this guy doesn't actually work. Work your way backwards. Do work on this because we're going to go through the answers on Wednesday, right? So you can see that we figured this out. It's not hard, but that's why I said, think about this. Right? Your answer is right in there in terms of what neurotransmitters I would use to accomplish the task I want to do. The best way to do this is to work backwards. Now, this is also known as an ipsilateral reflex arc. Because look at the signal. The sensory signal comes on the same side as the motor signal does. It's the same side pathway. So it's an ipsilateral, right, polysynaptic reflex. You're always going to have one set of muscles stimulated and the opposing group, the antagonistic group, inhibited. Now it's a simple one. Let's look at this one.
Are all polysynaptic ipsilateral?
Nope. Because what do you got right here?
Oh yeah.
Oh, this one's called a contralateral reflex. Because now it operates on both sides of the spinal cord. And here's why. If I were to step on a tack, right, I need to lift my foot up. Well, to do that, I have to contract my hams but relax my quads. But if I do that, I might fall on my ass. So I have to switch my weight or, alter my weight and support myself on the opposite leg, which means I got to talk to the other side of my body. So if I'm going to be contracting the hams on this side, I need to be relaxing them on the opposite side. If I'm relaxing the quads on this side, I need to contract the quads on the opposite side. So my sensory signal of, ouch, damn, that really hurts, unipolar, posterior gray horn, there's my synapse, interneuron talking to another interneuron, and these two interneurons, the white one and the black one, will each talk to a set of motor neurons. But if you notice the common pathway, see how the white one is always going to a solid black neuron? And then the white one talks to the black dashed one, and the black dashed one is always going to those blue dashed ones. So there's a uniformity in who's doing what over here. Think about just going backwards. How would I get the hams to contract on this side and the quads to relax on here, but yet on the opposite side, get the opposite to happen? Keeping in mind that a single neuron only releases one type of neurotransmitter. And just work your way backwards. How could I make this black one work, but yet not let the blue one work? And we'll go over these answers on Wednesday, right? It's pretty simple. It's not complicated. Just work your way backwards. But now we're also sending messages up to the brain. And these are what are known as spinal pathways. We're not talking about the different names of them up there. But this is why I'm now aware of the fact that I've actually stepped on something. I don't need to have this to know that I've stepped on something. Right? I can have no sensation at all of recognition. But the fact that I'm sending signals up to my brain, which is Wednesday's lecture, I will then be able to tell you, yeah, it's probably a stone or versus a piece of glass versus a bumblebee that I stepped on. You can kind of tell the difference, right? And that's because that signal goes to your brain and your brain says, oh yeah, I remember that. That's what a nail feels like or a rock feels like. But the important idea is to actually get your foot off of the danger, I don't have to involve the conscious part of my brain. It can literally be the spinal cord to the muscles, and I don't need to involve the brain. That's why reflexes are really quick and rapid. All right, last one. This reflex known as a Babinski. So, over here, this is what a baby should do, right? You're going to flare the toes outward when you take your thumb or keys or whatever and go on the bottom part of their foot and their toes flare out. They'll do that for the first year, year and a half of their life. Right? And that's simply because of the way the motor pathways haven't finished developing yet. But that's normal for them. Now, I should transition from a positive Babinski, where I curl or flare my toes outward, right? They call it dorsal flexion of the toes. From this to now curling my toes as an adult. So a 2-year-old on should be doing this. If an adult does that, I have neurological trauma. Something happened to my spinal cord or my brain because I'm not supposed to do that anymore. Right? And kids, babies, shouldn't be doing this. And it's simply just known as a positive and negative Babinski reflex. So up to a year and a half, we do this. After a year and a half, we take the adult path of just curling your toes or grabbing the towel. This just puts everything together for you guys, right? It's a visual of what I just did for you guys over here, right? You've got your unipolar neurons, right? Both somatic and visceral, right? Synapsing in the posterior or coming down, right? To an anterior. They don't have to involve an interneuron, or they can involve interneurons, and other parts could go up to my brain. That's why I just brought this to here and says, well, it could go here, it could go here, or it could go up to my brain. There's lots of different paths that'll go from that point on. Practice the idea that dorsal roots, right, as they say right there, contain sensory information, right, and anterior roots contain motor. Each one of those have to have both a visceral and somatic parts. And I can divide my anterior horn into somatic and visceral. And then I do the same thing over here. I'll have a visceral and somatic for my sensory nuclei. See, that's not much, right? You can learn that all in an hour.